Hello class 12th. 10th and 12th. Hello class 12th. In the last lecture we have discussed about the equation for the spherical surface. I have proved the concave one and I asked you to prove for the convex surface. Today we will discuss about lens, optical center, lens type and lens maker formula. Most important, lens maker formula. So let's get started. So let's start our first topic, lens. How to define it? Any transparent material. You can take any transparent material that can act as a lens, but conditions are both the surfaces of that transparent medium must be spherical. This is the condition one. And the second, at least one is spherical and second one plane. So condition becomes one, both the surfaces are spherical, and second, one is spherical and one may be plane. So that transparent medium will be called lens. And the lens is divided into two parts again. One is called converging lens, second one is called diverging lens. So how to define the lens which will be thicker in the middle and thinner at the edges, that will be converging, and the one which is thicker at the edges, thinner at the middle will be diverging lens. For that, let's see. These lenses are thinner at the edges and thicker at the middle. So these are all converging lens. But how to name it? Taking the first one as example. In this lens, the first side, this side is bulging. You can say convex. On the other side, and from this side again, this is bulging. So what you will name it? From that side it was convex. From this side it is still convex. So we will name it convexo convex. Convexo convex. Okay. So this is convexo convex. From first surface to the next surface, the name will be there. So let's see again the second example. What you will name it from this side? The first surface is plane, second surface from that side is convex. So we will name it plano convex. And the last case, the third case in the converging type, the first surface is like cave. So first surface is concave. The second surface from that side is convex. So what will be named? Yes, concavo convex. These all were the example of converging lens. Now let's see these three. These three are belonging to the diverging lens. So what will be the name? So first one is concavo concave, second one plano concave, and the third one convexo concave. So these were all about the type of lenses. So you can see the converging and the diverging actions. But how these diverging and converging actions are going on? Let's see for that. Taking the example first, for the convex and the concave, it is assumed that the lenses are made up of tiny prisms, a small number of tiny prisms. So taking that prisms, the action of prism is to take the ray and bend toward the base. So see, every tiny prism is bending the ray toward the prism. Okay, so that is why in the convex it is converging all the rays toward the base, and in this case for the concave one it is diverging all the rays toward the base again and again. But in the middle one of the convex and the concave both, you can see there is no refraction, no bending of light. Can you say why? The answer is the middle one, you can see, is acting like a small glass slab in both of them. So whenever the light falls on any glass slab, normally there is no refraction. So in this case there is no refraction and the light goes straight. But can you answer, is there was any ray? You can see here again, is there any ray in the convex or in the concave? Is there any incident ray is parallel to the emergent? Is parallel to the emergent, not in the line. So answer is no. No any ray is there. There is no any ray which is incident on the prism, incident on the lens, and after refraction becomes parallel. But we can take example the middle one of both the lenses, which can be assumed as a parallel. So if any ray incident on the prism and after refraction emergent parallel to the incident ray. So it must at least intersect the principal axis inside the lens, or it will appear to intersect. So that point is called optical center. In a short, we can say the incident ray and the emergent ray, if they are parallel to each other, then the light intersecting or appear to intersect the principal axis, that point is known as optical center. For that, let's see. In these two diagrams, in both the diagrams, the incident ray and the emergent ray is parallel and intersecting the principal axis at some point. So that intersecting point says optical center. And you can also see there is a shift between the incident ray and the emergent ray. Between the incident ray and the emergent ray. That is shift. We know that the lateral displacement is directly proportional to the thickness of the slab in that slab. Here the lens. So lateral displacement is still act as the same. The lateral displacement will be directly proportional to the thickness of the lens here. So suppose the lens is very thin. So what will be the lateral displacement? See here. If the lens is very thin, so the incident ray and the emergent ray almost are in same line. So we can say if the lens is very thin, there is no lateral displacement in the concave and the convex both. Clear? And again, so we can see the optical center for the convex and the concave both lie inside the lens. And see again for the plano-convex and the plano-concave, you can see the optical center is not at the same place. So in the plano-convex or in plano-concave, the optical center will lie on the spherical surface. Remember this, the optical center for the spherical plano-convex or plano-concave, the optical center will lie on the spherical surface. And in the next, for the concavo-convex or convexo-concave, in this case, in these two cases, the optical center will lie outside the lens. Say here, the optical centers are lying outside the lens, but on which side? The one side which is more curved. The side which is more curved, on that side the optical center will be. See, these were all about the optical centers, and used to it can ask in examination that where the optical center is lying in this lens or in that lens. So remember this. First, if it is convexo-concave, or you can say biconvex, so inside the lens. And if it is plano-convex or plano-concave, so at the surface but at the spherical one. And in the concavo-convex or convexo-concave, it will lie just outside the lens but to that side which is more curved. Our next topic is first focus and second focus. First focus may be any point. Don't bother about any point. Where is that? If the light is coming from that point on the lens, and after refraction those lines become parallel to the principal axis, so that point will known as first focus. Say in this case the rays are starting from a point, but after refraction of the lens they all become parallel to the principal axis. So definition says it is a point on the principal axis. If the ray is starting from that point, after refraction the rays become parallel, then that point will be first focus. So clear it is? Starting from this point, after refraction the rays are becoming parallel to the principal axis. So this point is called first focus. This was the case for the convex lens. But in the case of concave lens, the rays are coming from anywhere. So these all are divergent rays. So if they are coming on the prism, on the lens, so after refraction they become parallel. That point is accepting. See, all the rays are coming on the lens, and after refraction they are becoming parallel. But they are not starting from a single point, but it is appearing that all the rays are meeting at a point. So you can define it here. It is a point at which it is appeared. It is a point. It is appeared that all the rays are coming toward that point. But after refraction they become parallel. So that point will be first focus in the concave lens. What about the second focus? See this case. In this case, all the rays are coming parallel. So condition is first what? The rays must become parallel. Think about it. I am talking about the second focus now. That was first focus. So this case you can see all the rays are coming parallel, and after refraction they are coming to at a point, they are converging at a point. So if the rays in the starting was parallel, after refraction wherever they meet, that point will be second focus. And this was the case of convex. Second case for the concave, here you can say all the rays are coming parallel. So first condition is accepting, so all the rays are coming parallel, but after refraction they diverged. So where you will say the second focus. So see, all the rays are diverged, but they appear to start from this point. They appear to start from a point, not real point. They are appearing to start from a point. So that point at which it is appeared to start, after refraction they diverge. So that point will be second focus. Condition must be satisfied. For first focus, all the rays must be parallel after refraction. For the second focus, all the rays must start parallel toward the principal axis through the lens. And the distance from that point, first focus and second focus, whatever be the lens, the distances from that point to the optical center of the lens is known as focal length. Whatever be the lens, that will be. So the point from optical center to the first focus or second focus, that distance will be focal length of the lens. For the convex it is positive, for the concave it is negative. Now next topic that is most important for this year for your board examination, for 2021 examination, this is very important, and the topic is lens maker formula. Suppose any doctor is using any lens to cure the eye problem. So there is a curvature in the lens, the refractive index of the lens. So what should be the curvature? What should be the refractive index of that lens? So all depends on the focal length of the eye. So all these related equation is known as lens maker formula. So to prove that, I want to share one more important thing. We had started in the spherical surfaces with this equation to prove that n by v minus 1 by u is equal to n minus 1 by r. If in examination this question comes to prove the lens maker formula, so at least it will say the start from this equation. It will definitely give you start from this equation and obtain the lens maker formula. So don't forget this equation. So in examination either it will come to prove this one. For that n by v minus 1 by u is equal to n minus 1 by r. This equation will come to prove, or it will say that starting with this equation and obtain the lens maker formula. So we are going to prove the lens maker formula. Let's see in the sheet. Before starting the lens maker formula, I want to inform you that when for every lens, means the two surfaces, the image formed by the one surface will act as an object for the second surface. So keep this point in your mind, that image formed by the first surface will act as a object for the second surface. And let's start the lens maker formula. The principal axis, here it is the lens, but as I said, the image formed by first surface will act as the object for the second surface. So first I'm removing the second surface. I'm removing the second surface first, and see. On removing the second surface, so at this time consider this area, means this side as refractive index n1, you can consider as air, and this area means the other side now as having the refractive index n2, the other side. But this lens currently it is appearing like the spherical surface of the convex surface of any different medium. So using that topic, I'm doing again. Now let O as object on the principal axis, one ray starting from point O falling on the spherical surface, and it will bend toward the normal as n2 is the denser medium. So let's do that. First draw normal. So this is Cn1 is the normal, means C is the center of curvature, and now the ray, means light, will bend toward the normal in the second medium. Let's see what happened. And now consider this is the position of image. Why I'm using the pencil? Because there is a second face, second surface, but I'm using the pencil means I'm showing you the image formed by the first surface. So image formed by the first surface will act as the object for the second surface. So first of all, let's write the positions and the distances. Object distance u, image distance v, the radius of curvature r1. I'm pointing this point with C1 because there is another surface after some time. There will be another surface. So that will be C2. So I'm naming it the C1, and the distance from pole to the center of curvature will be R1. So using this, it is acting like convex spherical surface. So for the convex spherical surface, we can write one equation, see here, and that equation is n2 by v minus n1 by u is equal to n2 minus n1 by r1. R1 because for the first surface. N2 means the second medium refractive index. N1 means the first medium refractive index. The light is going from first medium to another. So second medium upon v, first medium upon u is equal to second minus first upon r1. But now I'm making this as a equation 1. I'm telling you that there is another surface here. Now this is the time to draw the second surface. So here it is, the second surface. Now you can see the light is going through this way, then it passes through this, and now the light will not go anymore on this path. So this image will act as a virtual image and act as object for this surface. So where this light will go further, for that I have to draw a normal on this side. For this surface, the normal will drawn on this side. Let's do first those things. So this is C2 and 2, another normal for this surface. And I said this image is not real anymore. So I'm naming this as I dash. So this will be virtual image I dash now. So this distance is not real anymore. So I'm naming this also V dash, not real and anymore. So N1, say N2, N1 to N2 when it was. So I had written N2 upon V. So this was V. Now this V is now V dash. Remember this, for this surface, the image is from virtual, so distance changed to V dash. So I have written here N2 by V dash, N1 by U is equal to N2 minus N1 by R1. This was equation 1, and I have changed this because this is virtual image. For that virtual, this must be dotted line. I'm drawing that. Again, listen my point. The image formed by this surface is this. Now there is another surface, so this image will be virtual. So this virtual image will act as an object for this surface, and taking this surface only, the first surface only, I have written the equation second medium upon image distance, that was V dash, then first medium upon object distance, that is u, and second medium minus first medium upon r1. If you have proved the relation for the convex spherical surface, so I think you know this equation. Now for the second surface, let's draw the image, because the ray is going through this, then it bends toward the normal. Now it is going from second medium to first medium again, means this medium again becomes n1. So it is going from second medium to first medium again, so it will go away from the normal. So this is the normal for the second surface, and it will go away from the normal somewhere in this direction. So let's draw first. Now see, this was the object, this ray, after bending toward the normal comes to here. Now it is going to change another medium, so it is going away from the normal, and this is the final image. This is the final image, this is the virtual image. So this object forms the real image here by using both the surfaces, and this image as a virtual only using for this surface. Now let's write the image distance from this surface, because this image is formed due to this surface. So image will be written from this to this distance, and the radius of curvature for this one is from this point to this point, because for this surface it is. So let's write that. So I have written here the center of curvature for this one from here to here, and this is the final image.
due to this surface. So distance will be measured from this point, means this point to this point. So this is final V. This was V dash. So we have written this equation using the first surface. Now we are going to write the equation for this surface. So see, the light is going from N2 to N1, and this is the concave spherical surface. The equation is same for both, is convex or concave, but this time the medium is different. Here it was going from first medium to another, like N1 to N2. Here it is going from N2 to N1, means second medium to first medium. So instead of writing N2 upon N1, here second medium is N1. So N1 upon V, image distance. So what is here V? This one. So let's write that first. See here, N1 by V. Here it was N2 by V dash. N2 means second medium. V dash means image distance. Here N1 means second medium because light is going from here to here. So N1 is now second medium here, and image distance is V. This one. Minus N1 upon U. N1 means first medium. For in this case, the first medium is N2, and N1 upon U means object distance. Here, listen carefully. This is the second medium. This is the first medium. So refractive index of first medium upon object distance. So this is the refractive index of first medium will act as a here. And what will be the object distance in this case? I said the image formed by the first surface will act as a object. So this distance from here up to here, and I want for this surface distance from here only to here. So what to do? Let us consider the thickness of this lens be small t. So I'm considering this. Let the thickness of the lens is small t. Now we can calculate the distance from here up to here, that V dash minus t will be distance from this point to this point. Why? Because you have to write the refractive index of first medium upon object distance. Here in this case, the refractive index of first medium is N2 and the object distance is from here to here. So to calculate that means V dash minus t. Let's write here. See here. This was the refractive index of second medium. In this case, refractive index of second medium. This was the refractive index of first medium. In this case, refractive index of first medium is N2, and the object distance imaged by the second surface will act as an object. So here the distance of the object in this case is equal to N1 minus N2 upon R2. Like the medium is reversed, so N1 minus N2 upon R2. Now consider the thickness of the lens is very small, means negligible. So small t can neglect. So we can write this equation without t. I am considering the t is very small. So this equation can be written as N1 upon V minus N2 upon V dash. T is negligible. N1 minus N2 upon R2 for very thin lens. So see from this equation and this equation, N2 upon V dash here and N2 upon V dash here also. Let's add both the equation and let's see what will happen on adding N2 upon V dash minus N1 upon U written here plus N1 upon V minus N2 upon V added is equal to N2 minus N1 upon R1 plus N1 minus N2 upon R2. So you can see N2 upon V dash, N2 upon V dash same, that will be cancelled. So N1 upon V minus N1 upon U remaining. And see here N2 minus N1 and here N2 minus N1 minus N2. If you will take minus common, so numerator will become same. Let's see here how. Now see here, remaining part is N1 upon V minus N1 upon U, N2 minus N1 upon R1. I have taken minus common, so it becomes N2 minus N1 upon R2. This is minus common. So in the here N1 is common and here N2 minus N1 is common. Let's write that. Here we go. N1 common, 1 upon V minus 1 upon U is equal to N2 minus N1 bracket 1 upon R1 minus 1 upon R2. Now take this N1 on that side. Now see, on taking N1 on the other side, 1 by V minus 1 by U, I have divided N2 in both the parts. So N2 by N1 minus N1 by N1. So N1 by N1 will become 1. What remaining? N2 by N1 minus 1. See again. So this becomes N2 by N1 minus 1. N2 by N1, refractive index of second medium upon first medium, is just the refractive index of this medium, means N2 upon N1 means the refractive index of this medium only, means of this lens. So we can write here only N and see what happens. Here we go. Now, after this equation, let this equation be 3. Tell me, when the object is at infinity, when the object is at infinity, where the image forms? The answer is image forms at focus. You can see in this diagram the object at infinity and the image forms at focus. On putting that here, let's see. So we can say if u is equal to infinity, so v is equal to f. Let's fill that. So on filling the value, 1 upon f minus 1 upon infinity is equal to remaining same. 1 upon infinity is 0. So what remaining now? Finally, it comes to 1 upon f is equal to n minus 1, 1 upon r1 minus 1 upon r2. Actually, this equation especially is known as Lensmaker formula. This is the special equation known as Lensmaker formula. Now again, just compare this equation 3 and this equation 4. On the right side it is same, but on the left side can be equal. So on writing that, on comparing, see again, left hand side this one and left hand side with this one. On comparing, we got 1 by f is equal to 1 by v minus 1 by u. The proving the derivation ends here. Lensmaker formula. That's it. In examination, you have to prove up to this only. But on comparing the left hand side, it comes to 1 by f is equal to 1 by v minus 1 by u. You have seen this in class 10. This equation is known as Gaussian form of lens equation, and the proving is only up to here. It ends here.
So we have seen the two equation, one Lensmaker formula and its Gaussian form of lens equation. Here I'm ending the session. Next lecture we'll see further. I want from your side that to solve all the numericals and inform you if you're facing the problem. Till then.